Today's topic is word embeddings. First of all, let us see what is the need of word embeddings. We'll of course see what does it mean by word embedding, but just to give you context. So for um, algorithms like machine learning, deep learning, or even statistical techniques to be used, the inputs are numbers, right? In statistical techniques or in machine learning, say like regression, classification, we do numerical computation. So you take set of numbers, you multiply them, have some formula on it. Even in deep learning, you apply weight matrices multiplication on it, and then do the neural network based computation. So the basic premise for all machine learning, deep learning, or even statistical techniques is that you need numbers. Unless numbers are there, you cannot do the current machine learning or deep learning. So typically for machine learning, deep learning like AI techniques, typically they work on a set of numbers like we have numerical tables. You can apply machine learning and deep learning on top of that input. You can apply machine learning and deep learning for on images, right? For image classification, image segmentation, detecting objects in images. You can apply them on sounds, videos. But as you can see, numerical data is of course numbers. Image data, if you can closely see, they are nothing but numbers only. They are matrices of numbers. Images are pixel values actually. Sound is also a set of numbers, set like a time series. Videos is set of images, again numbers. Only one modality, only one data type that we often use and is not numbers is language, words or sentences. These are strings. They are a set of characters. So can we not apply machine learning techniques or deep learning techniques on text or words? So if I want to find out, given a text, is it a positive text or a negative text? Like sentiment analysis. Can I not apply machine learning or even statistical techniques on it? I should be able to, right? If I want to summarize a text, so input is a big text and we want output as a small text. There also, typically machine learning, deep learning techniques are used. But how can I feed text, that is words and sentences and documents, to these machine learning or deep learning algorithms? It is not possible directly unless you convert them to numbers. Unless you convert text to numbers, the further processes like statistical techniques or machine learning or deep learning, they are not possible. So the main objective of this session is to talk about techniques related to conversion of text to numbers. By the way, this process of conversion of text to numbers is extremely fundamental. This is the bedrock. This is the fundamental technique that then builds on word embeddings, then that is used in large language models and all the popular generative AI language-based techniques that we are seeing today. So this is a fundamental topic that we are discussing today. So the whole objective of this session is to see how to convert text to numbers. While doing so, how good can we convert text to numbers? And we'll see what that goodness means. Okay. So word embeddings. So assume you have a word. So word embeddings is nothing but the word embedding has slightly different meaning. I'll explain that. So word to vec. So it's a word to vectorization, word to vector conversion. Another name for same thing, vectorization, meaning text to vectors. Vectors is nothing but set of numbers, right? Array of numbers. So word embeddings is basically word vectorization, word vector only. Now this word again is abstracted loosely used. Document vectorization or sentence vectorization. The process is same, text to numbers. So how good we convert that word or text to numbers is what we are going to see today. What is a good vector representation? There are certain criteria. It's just not good that it looks good or whatever, because from a sentence or a word, we are converting to set of numbers. How good this conversion is. So there are certain criteria that we are going to see. The basic idea is if I convert similar words to numbers, meaning vectors, in the vector space, I'll explain that word vector space thing. They should be near. Okay, this is the basic premise. So if I'm talking about two fruits, two type of fruits, say apple and a banana, their vector representation are these vector representations when represented in vector space, nth dimensional space, are these 2 points near to each other compared to if I have vector of mango and an elephant. So one is a fruit, one is an animal. If I get their vectors and I put them in vector space, nth dimensional vector space, their point representation should be away because they are not similar things. So similar words vectors should be close in the vector space and dissimilar words vectors should be away. So this is the basic test. So there are multiple approaches to convert text to numbers. But then how do we choose which one to use? Based on this goodness criteria. Goodness criteria is, I've mentioned just one as of now, and that is the basic one. Similar, semantically similar, meaning-wise similar, category-wise similar, type-wise similar. Words, vector representation by certain method, or that method, then they need to be very close. So that's the idea. I'll explain that vector space idea also. All right. So as we are saying, another level is, of course, to capture relationship that we will say. Now, why I'm saying word vector and word embedding is same. This embedding word is a little tricky. Embedding is meaning putting something in place, right? So assume that you have a vector of say 3 dimension, meaning x, y, z. There are 3 numbers in it. Can we represent this vector as a point in 3-dimensional space? Yes, we can. X-axis, y-axis, and z-axis. So just imagine a vector is actually a point in nth dimensional space. So if length of the vector is 3, then it is 3-dimensional space, 3D space. If the length of the vector is 2, xy only, it is a 2-dimensional space. If the length of the vector is 300, then it is 300 dimensional space. Of course, we being mere mortals, we can only see or visualize only up to 3 spatially. 300 dimension we cannot visualize, but at least we can imagine. So there are 300 axes. In that there is a point. And that point has coordinates, 300 coordinates, right? Not just x, y, z, but up to 300. So this is the way to imagine. So why this is called as why word vector is called as word embedding? Embedding is nothing but the point representation in nth dimensional space. That's the basic idea. Now, another thing to look at it, this is a very fundamental concept that one has to see. Now there are two vectors. when they are plotted in their nth dimensional space, are they close? Meaning distance between them, is it small compared to if they are dissimilar words vectors, they should be away, meaning distance has to be large. That's the idea. So how do we find if these two vectors are very close mathematically? There's a Euclidean distance that typically everybody knows, those who have done up to 10th. Or there is another thing called as a dot product. This is nothing but angle. So if angle is very small, they are sort of collinear, very close. Right? So this is the mathematical computation. Either Euclidean distance or any type of distance. There are multiple types of distances. Euclidean is the raised to 2 kind of distance, or cosine similarity. If they are very close numerical here in the embedding space, their distance between them is very, very small. So we should be able to imagine a vector as a point. That's the whole idea of explaining this slide. So down in this session, I will use the vector representation and its equivalent point representation interchangeably. Okay, now how do we decide for a word if I want to have 3-dimensional vector, 5-dimensional vector, 300 or 2000? Actually, it's a choice based on the computation, memory, and other things. But just keep it in mind that it's up to us. Now, it is very easy to see that the longer the vector, it will be able to capture the meaning better. Right? More the merrier. But there is a downside. To store this vector, we will need more memory. To compute cosine similarity, Euclidean distance, more computation. So there has to be some break-even thing, some balance. Not too long, not too short. So typically, many things, whatever you see, they are 300 long or typically 1024 kind of 1K kind of long. So there are some standards that people follow. So not too short, not too long. So N is in our hands. All right. So there are two major approaches in converting text to numbers. So there are statistical, traditional, frequency-based approaches, which is sort of oldish, and there are newer, more popular. I wouldn't say more popular, more fashionable. Machine learning and deep learning based approaches. We are going to see both. Okay. So traditional, I'd say frequency based or statistical. Two examples that I've mentioned here. One hot encoding, bag of words kind of approach. And one variation of it called TF-IDF, term frequency inverse document frequency vector. These are two very popular approaches in case of statistical techniques. In case of neural network, modern techniques, word-to-vec is very famous. Then, of course, GLOVE, Stanford, BERT, and of course, the transformers that we get to see these days. These are all modern neural network or transformer-based architecture-based word vectorizations. Again, the idea is to convert text to numbers, and there are many approaches. Some are statistical and some are neural network based. We'll first see the statistical ones. By the way, I've worked in this domain for quite a few years. Even though there are certain problems with frequency-based or traditional approaches, they're still useful, at least to do initial checkup or whatever, proof of concept, because they are fast, quick, but they have other disadvantages also. And the point of telling is, even though modern approaches have been coming day by day, the old approaches haven't lost their relevance. They're still practiced. Only thing we have to know their downside also. So we'll see traditional approaches. Now, just imagine, think for yourself that you want to convert text to numbers. So there is a word, cat or a dog. How do you convert that to numbers, set of numbers? Just imagine. How can you do that? One of the crudest approach, I would say, assume that you have an English dictionary, 3 million long, so there are 3 million words assume. So there's a 3 million long word. So basically take an array of which is 3 million long. Put all the indices, all the positions as 0. So for word cat in the dictionary, if the cat happens to be 500th word, okay, in the dictionary, right from beginning, ABC, cat happens to be 500th word, then 500th position in the 3 million long 0 vector, put there 1. Getting my point? For cat, cat's position in the dictionaries is 500. So in the vector, the 500th position, I'm putting at 1 and rest everybody 0. So this is the vector representation for cat. Similarly, dog could be 700. I'm just taking some numbers. So for dog's vector, it is again 3 million long, all zeros except 700th position, index. Index and position I'm using interchangeably. Getting my point? So this is the crudest way of representing words to numbers. I've given some example here. Of course, this is not very dictionary based, meaning Rome does not have is not the first word in the, but assume there's some scheme that I have only 100 words and Rome is the first word, right? So this is the way, this is called as one hot encoding because only one position is hot, meaning one, rest all are 0, cold. So this is how in the crudest form you represent word to vec. There are two major problems with this approach. By the way, just see, and I'll discuss those problems. Rome is represented this way. In our vocabulary, by the way, you need not have 3 million long vector all the time. If your vocabulary, the domain in which you are working, if it is of only 100 words, you're not bothered about any other words, then your vocab is of 100. Your vector size will be 100. There you would assign that Rome is first, Paris is second, something of that, right? So this is how you represent Rome as vector, Paris as vector, Italy as vector, and so on and so forth. So two major problems that I mentioned is it takes a lot of space, memory, isn't it? If your vocabulary is really 3 million long, then your word vector is 3 million long, maybe in some MBs and GBs probably. And then doing computation on top of it, finding the similarity between Rome and Paris, meaning doing cosine similarity between 3 million numbers versus 3 million numbers, right? Too much. So memory is too much and computation is too much. But it is very simple way to calculate. No calculation as such, right? Only putting a particular index as 1, rest everything 0. So com for me, population wise, it's very easy, but computation, meaning processes on top of it, plus memory, it is gone. Another problem. So now that we have word converted to vectors, how do you convert sentences? Again, a very crude approach would be take vectors of each of the words in the sentence and take average. Very crude way, right? So we'll see that is called as bag of words. All right. So another set of example. We have motel here. Assume that motel's representation is above and hotel's representation is below. Now our initial test of a good vectorization approach, good embedding approach is that similar words should be very close in the embedding space. Another way to say is that cosine similarity between vectors of two similar words has to be 1, or angle has to be 0. Cos 0 is 1, close to 1. Right? Cosine has to be close to 1. 0.9, 0.95 is close, meaning they are very similar. Now, if you take cosine of these two vectors, it's probably exercise at home, is it close to 1? No. By the way, if you do cosine similarity between any two vectors following one hot encoding, the result will be similar. So that way, this is not very useful. Another thing is that, again, as I mentioned, space is too much, computation is too much, but computation also is not very meaningful. So this is not really a semantic representation. This is not a meaningful representation, although it is very easy to populate. And we want these to be similar because in a chatbot, while processing language, I am staying in Seattle motel. I am staying in Seattle hotel. More or less, they mean same thing, right? More or less. Motel and hotel. Of course, there are some nuances as far as hospitality industry goes, but they are more or less similar. But in our embedding space, they are orthogonal. They are like 90 degree apart. That's not useful. So some extension to set of numbers, meaning sentences or documents. So here I've taken two examples. D1 is actually very small document itself. Although documents are very long, I'm considering these two sentences as a part of a small document, D1. Another document is D2. What is the vocabulary? Basically a union set of D1 and D2. So these are the words which are common in our union set of this. By the way, tokens and words are used interchangeably as of now in this session, but once we look at large language models, there are differences. So for now, let's call words as tokens only, same thing as of now. So D1 is represented now, vocabulary long vector has to be there as we saw. So there are 6 words totally, considering both D1 and D2. So D1 is represented that way. So in D1, he appears 1. So this is a frequency-based vectorization. Frequency, not position, frequency. He appears 1, she appears once in D1, lazy twice, something like that, right? You're getting it. Now this is a little better. Now, with this representation, this is called as count vectorizer, bag of words also. Now with this, we can find a similarity between two documents now. Is D1 similar to D2? Why do we need this? Let's take an example of plagiarism, meaning somebody has copied something from somebody. One essay is there, another essay is sort of copy of the same thing, right? Changing few words on here. If we want to automate the process of checking, if these two documents are very similar or close to each other, then we would represent D1 like that, D2 like that, and find cosine similarity, ideally, if the representation is good. So, document represented as word. Word to vec, we saw word represented as vector. Just extension of that concept, set of words, meaning document represented as vectors is also possible. So, this is the way it is represented. And we can do cosine similarity and other approaches. Once document is converted to numbers, D1 is converted to numbers, D2 is converted to numbers, then cosine similarity is possible, Euclidean distance is possible, feeding them in machine learning algorithm to find sentiment analysis is possible, feeding them to deep learning neural network is possible. Once these are numbers, then we are good to go as far as machine learning, deep learning is concerned. So, a very abstract representation, I'll just let you Go over it yourself. So if there are 8 documents, and totally assume that there are 8 words, there could be more, hundreds of words. So term 1, term 2, term 3, term 4. So this so-called vertical thing, that this could be words, and the horizontal one that we are saying is documents. So as you can see, document 4 has four terms, right? Like that. And you got it. So this is how count vectorization can be represented. Little more refined approach, same thing, count vectorization only, but it solves one problem of count vectorization. Count vectorization is very sparse. So in a document, say if it has few words, rest of the positions remain 0, right? Not useful, sparse. It is not a dense vector. So memory is gone, the computation is gone, too much of memory and too much of computations. To avoid this formula has come in, this approach has come in. This is called as TF-IDF, term frequency inverse document frequency. What does it do? In a document, for a word, it computes how many words, how many of this word are there in this document. That is called as TF. Basically, for each word in a document, we find weights. So W is weights. Little complicated formula, but it is not complicated, easy to understand. For ith word in jth document, basically for word in a document as of now, we are calculating weight. So TF is nothing but turn frequency. How many times this word appears in this document? Another number is this word appears how many times in other documents. Right? That is DF, number of documents containing I. So in my document, if the word cat is 4 times, so the TF is 4 for this document. If the cat happens to be 15 times in all other N documents, that is 15. Okay, and N is total number of documents. I'll give you intuition. The intuition is if there are very common words like a and the, then they'll be there in this current document also many times. They'll be there in other documents also many times. So this being an inverse log formula, their weight comes out to be very small. Okay, as their weight is small, all these so-called common words, they have very small weights. But if the word is very unique to this document, if this document is about politics, and if say word Trump appears only twice and not much in other documents, so this is a very unique word for this document. So its term frequency is a 2, but it is not there in other documents, so its weight is heightened. So its weight becomes high. In this approach, we have a choice. Instead of all 3 million weights, 3 weights for 3 million words, we can have a cutoff that I want to look at words with weights sorted only up to 100 words, 1000 words, or weights above this, and we just ignore the remaining ones. Meaning, we have a vocabulary of only unique words. All a and those are just discarded and they're assumed not to be there, they're just not counted. Okay. By this, we have solved the size problem, the computation problem. But to arrive at that this representation, we need to do some computation. So there's some trade-off here. Again, both frequency-based, meaning count vectorizer approach, and this approach is frequency-based. Anyway, one major problem that TF-IDF solves is it can reduce the size, but one major problem still remains in both count vectorizer and TF-IDF is that for a sentence, the order is lost. right? Because we are just counting the frequencies. We are not saying, so meaning cat sat on a mat and mat sat on a cat. Their both representations would be similar. So the relationship thing, the orderness, which is very necessary in languages like English, is gone. So frequency-based approaches, they suffer this disadvantage. And another disadvantage, of course, TF-IDF reduces a bit, but other thing is the memory is long, and then the computation is long, and the sparseness is long. So what ideally we want vector size to be small also, reasonably small. We want it to be dense, meaning not zeros here and there. And we want it to have meaning. And we want it to have relationship preserved, meaning order preserved. All these aspects are catered to by the modern approaches, which are neural network based approaches. And we see those. So a good representation that I just mentioned is shown here. I'll wait here. So we want to see a good representation that is semantic is nature, preserves the relationship, is small and dense. Okay. Now there is a theory called distributional semantics. We'll look at that. How to get the meaning, semanticness. The theory tells that if I want to know about a particular word, I need not know about that word. But if I get to know about its neighbors, its context, its neighborhood, then I can know the meaning of this word. I'll repeat. If I want to find out meaning of this middle word, I need not know its meaning. But if I know the meaning of its other words, then I can find out the meaning of it. So distributional semantics, distributional embeddings use this basic principle of neighborhood, and the neighborhood is called as context. Okay, we'll see how it is arrived at. This is a very interesting theory. I'll take one example which will make it clear. So if I ask you, what is this? What is the meaning of this word? Bardwak, Bardwac. Nobody knows. Even I don't know. There is no meaning also. But if there is a word like that, there's some foreign word which has come to English, then how do we find meaning of this word? Now the distributional semantics says that look at its neighbor. There is a very common proverb. If I want to know about a man, I just need to know about his company. Company meaning his friends. If I know about a certain person's friends, I can find out the person. So that's the basic premise of this approach. Okay. Now let's look at some examples. Just go over it once. I won't be reading. Just go over it one by one. Now, instead of asking meaning of Bardiva, now I am giving a context. Just by looking at the context, you sort of guess what is the meaning of Bardiva. Bardiva is not the word. Still, you know what it means. That's the idea of distributional semantics. He handed her a glass of Bardiva. Beef dishes are very good. Something. I dined up. So you sort of know what Bardiva could be, isn't it? So it appears that there is some drink like that, which is rare and made up of grapes. Context helps, although the word is irrelevant here, and the word is actually not there. This is called as distributional semantics. How do we use that? Why are we studying this? Because now we will formulate words vector by vector of the neighbors. And the vector of neighbors also, how do we get it? There's a chicken and egg problem, but we'll see the approach. But the basic idea is if I want to get the words vector, if I have neighbors vectors, I can form my vector. That's the idea. Because I am represented by my neighbors, my context. This is the principle used in a very famous word embedding technique called word to vec. Word to vec was invented by Timothy McLaugh, I think, Tim McLaugh. He was intern in Google. He wrote this paper, Word to Vec. Very famous. This, in my opinion, is the watershed movement in NLP, natural language processing. There are other techniques, but the word to vec is neural network based technique. There are other techniques like co-occurrence based techniques. GLOW is one of them, Global Vector Representation, GLOW by Stanford guy, I think it's Richard Socher. So we will see word to vec which explicitly uses the neighborhood information. Globe also uses neighborhood information because it is based on co-occurrence. Co-occurrence meaning if I'm there, these also guys are there. That kind of method. But we'll see word to vec closely. I'm going to explain these approaches in more details so that you get it. This is the core of word to vec, the modern word to vec. Of course, transformers are more famous these days, but this is what made the revolution. So there are two ways in converting word to vec. Okay, so there are two neural networks possible. Okay, one is called as continuous bag of words, CBOW. It has been shown here. This is the neural network. Actually, it's a very simple neural network. Only one hidden layer, one output layer, and one input layer. Inputs basically, one hidden layer. So CBOW, continuous bag of words, what does it do? If I have 5 words long sentence, I want to find the middle words vector. I make it as output. And all the 4 words, which are my neighbors, I make them as inputs. So this word in the middle word has become the output. And my neighbors have become inputs. Now these neighbors are words. Okay. We cannot use words as is directly in neural networks. Obvious. So we take a one hot encoding of it. One hot encoding is possible. This is 5 word long vocabulary 10000010, something like that, right? So one hot encoding of this word, one hot encoding of this word, one hot encoding of and output is also one hot encoding of the middle word. Initially, they are one hot encodings. Here comes the genius part. Okay, the middle hidden layer is the representation that we are going to compute. Okay, now the length, the number of nodes here is up to us. That is the n, the length of the word vector. Okay, assume that it is a 5, 10, whatever. Okay, one hot encoding multiplied by a weight vector here. Those who are familiar with deep learning would easily understand. This vector into weight vector will give this. This vector into word vector will give this. Now there will be a difference because we started with random weights. The difference is back propagated till everything is settled. Once settled, the word, this vector representation is in the middle, is the vector representation of this word. This is the approach. This is called as CBOW, continuous bag of words. What does it mean? Meaning I have such vector representation which, given the inputs, neighbors, give me output, same word. That's the idea. Once you understand this idea, everything is just details. Again, I'll repeat. I started with one hot encoding of my neighbor words. I made myself as output, and I did neural network epochs, backpropagation till the time the prediction comes right. From these inputs, I have to get this output prediction. The middle hidden layer, which helped me convert inputs to output myself, is my representation. This is the basic principle. Similar to CBOW, another approach is skipgram. Little hard to intuitively understand, but it's actually the same thing. Now I'm seeing myself as input and my neighbors as output. Again, same thing. I do backpropagation epochs. Then after settlement, whatever the middle hidden layer is, for which I decide the n, that's my representation. So here neighbors giving myself as output, myself as input, given neighbors as output. Both actually are diametrically opposite but doing actually similar things, isn't it? Both yield the middle hidden layer, which is the vector representation of this world. This was as I said, a revolutionary moment that was proposed. Now, what has happened? If you compare with the frequency-based approaches, you can easily see we have solved many problems. We have reduced the length. Length is actually up to us. The hidden layer, it is 5 nodes, 300 nodes, 1024 nodes is up to us. So we decide the length, not the vocabulary. This being neural network, actually it becomes very dense. So the sparseness issue is gone. Are we considering semantics meaning neighborhood? Yes, because we are building myself on neighborhood. So all those concerns are gone. So this is a wonderful revolutionary technique that was proposed. When I started on this journey, this was the approach we used to use very heavily. So word to vec, it's available in library called GenSim, Python library, and it's sort of an extension called doc to vec. We used heavily in our so-called childhood. All right. So one more way of representing the same thing, you can easily see these are input neighbors, input vectors for neighbors. All four are going in, right? Then hidden layer is nothing but the word vector. Some again multiplication. This blue and green are the weight matrices, and this is the output. We are trying to get myself as output using the neighbors till all the epochs are done. So the H becomes vector representation of this world in CBOW. Again, as I said, diametrically opposite but similar thing. Myself giving output as neighbors, myself generating neighbors. All right, I'll wait here. Just go. Not much important. By the way, you don't have to know this by heart. There are ready libraries that give us these, but it's of course good to know the theory behind them. So word to vec was major improvement. As I said, all the advantages are there. Glove, probably you can read up. This is basically co-occurrence matrix for a word. Out of vocabulary, how many are close to me? Co-occurrence matrix is calculated, and then actually, I think LU decomposition happens, the matrix split happens, and then you get the word representation. But if you have understood word to vec, that's good enough as of now. That's the main concept I wanted to cover. Then now we will see. Okay. Now we'll see some later approaches or later architectures that used for a word to vec kind of approach or word embeddings approach. And then later we'll see the applications basically. Another important milestone that came in the picture is called BERT, bidirectional encoder representation. I'll just give you an idea of how it is made. Assume that you are doing machine translation, English to French. Okay, so there is an English sentence and there is a French sentence. There are multiple such pairs, English, French, and then you train an encoder-decoder network. Okay, those who are familiar with sequence to sequence kind of neural networks, this is how it is trained. And then this encoder, it can be RNN cell, LSTM cell, typically LSTM cells. And then on output decoder side also, RNN or LSTM cells. So encoder encodes English sentence into a middle representation called latent representation or hidden representation, and then hidden representation then generates the output. But during training time, both inputs and outputs are available in one hot encoding form. All these neural networks are trained multiple epochs for all the pairs. Then we get a model which is encoder decoder model, which is able to convert any English sentence to any French statement, right? So far, okay. And sometimes they are unidirectional and sometimes they are bidirectional also, meaning both sides. This becomes input, this becomes output, this becomes input, this becomes output. Only encoder part of it, if you just focus, it takes English sentence and gives a latent or hidden representation. This representation is nothing but this input sentences vector representation. So another way to look at it, a sentence has been converted to vector. That's why this is again a word vectorization method. This vectorization method is bidirectional encoder only. Once the training is over, we are forgetting the decoder. By the way, machine translation is just one way of doing this training. There could be other ways. Bidirectional encoder represented BIRD is extremely famous way to convert text to numbers. Right? And as I said, for pre-training, meaning actual training, it could be masked language model. We'll see them in transformer. Transformer architecture that we are going to see next time is actually BERT-like. BERT is just probably some layers. This is 6 layers and 6 layers in transformer, but trained on multiple tasks. It's just not machine translation like task, but masked language representation. This sentence and the next sentence prediction need not be English and French. Current sentence and the next sentence prediction. That way also you can train. But for usage, you keep only the encoder part. So this takes a sentence and gives a vector representation. Done. Once we have vector representation, you can use it for cosine similarity, machine learning, deep learning, and any other thing. So this, apart from word to vec, BERT is again a milestone way of doing things. And the third milestone is, of course, the paper attention is all you need, which is sort of like BERT only, but of course, very elaborate architecture and more parallelized architecture. We'll see that in the next session. So the current ones, recent advances, I won't go through them, just have a look at them. This billion parameters is nothing but the weights in the neural network. So nowadays, models are coming up with 175 billion, all those parameters. All right. Now it is interesting to see once text is converted to numbers, we saw one property. If they are semantically, meaning-wise very similar, then their cosine similarity is very close, meaning 0.9 close to 1, and their embeddings in the embedding space, they are close. The distance between them is very small, isn't it? There's another property which was extremely surprising, which is mentioned in Tim's paper, word to vec paper. And I'll show you that property. This is the one that you can see. So assume in the 2D space, King's vector is shown here. Okay. In 2D, this is a XY, only two XY two-dimensional vector for King. Similarly for Queen and Man. So If these vectors are plotted this way, it was found that the distance between king and queen, okay, I have plotted, by the way, this is a positional vector of this point. The difference between them is nothing but this. This is a vector algebra thing. King minus queen is nothing but this difference, this vector. If I take this vector and put it on man, from man I start this vector, same vector. I just transport this vector here and put it here, then add the corresponding queen's point. I get woman. Can you see the revolution here? So king's female counterpart is queen. So king plus this difference gives me queen. So if I take this difference vector and put it on man, it gives me women. So it has understood the meaning of the feminine representation of a masculine word. This was a revolution, meaning it understood the meaning of the word, right? It understood the semantics. So it is obeying laws of vector algebra, not just similarity, but vector algebra. So that's why these words have meaning in them. All right. So these examples as I, so king to queen, that difference, if you put it on man, will get woman. If you put it on uncle, will get aunt. Aunt meaning aunt's vector representation is very close to this difference. So this is how now this works in the gender relationship now. Apart from taking neighborhood information, now these vectors are showing relationship information. Gender relation they are exhibiting. They're exhibiting plurality also. Of king and kings. This difference, if I put it on queen, it gives me queens. And there are more wonders than this. It shows the relationship between country and its capital also. So this, as I said, word to wake was a watershed movement. So just imagine a set of numbers have captured the meaning of that text. And now, as the vector representation is extremely meaningful, not extremely, actually reasonably meaningful, the sentiment analysis that you'll do, the intent classification that you'll do, the summarization that you'll do later in using machine learning or deep learning will be meaningful if you had used frequency-based approach, which is 0101, those kinds of bag of words. There was no relationship, there was no meaning, the word size was, the vector size was long. Their usage, their meaningness would be very bad compared to these approaches. That's why these approaches are very, very powerful. Some examples here, some comparison. Just have a quick glance. That's about it. This is what I wanted to cover. We'll quickly go over the applications. Now that we have vectors for text, the world of machine learning and deep learning is open to us. Many applications are possible. Similarity. Now, where does similarity come in the picture? So if you're doing typing and you misspelled a word by a character or something, right? It gives you all the options, right? The spell checker gives you all the. How does it find? Of course, there are different mechanisms, quick indexing kind of mechanism. But assume this is almost like a. It is trying to find very similar word, isn't it? So if you plot think, thought, ponder, pondering, the nth embedding space, these points will be very, very useful. Why this is necessary? Because in chatbot, if you're typing, I thought, I'm thinking, all this actually mean the same thing, right? So the answer after vectorization should bring the correct answer. So that's why meaning is important. Machine translation, now it is very meaningful. Uh, it understands English well, it understands French well, so it is easy to do the conversion. Parts of speech, all the NLP approaches that we saw last time, those are typically now those typically now use machine learning based approaches and deep learning based approaches. And there the essential condition to convert text to numbers is done by these approaches that we saw today, word-to-vec or transformer-based approaches. Another thing is sentiment analysis, nothing but all the text and there is sentiment 0, 1, 0, 1, 0, 1, positive, negative, positive, negative. That is now possible using simple machine learning algorithms like naive Bayes, random forest, SVM, decision tree. I'll take just a quick example. Let's do if you want to do tweet sentiment analysis, whether this tweet is positive or negative. Now this tweet cannot be fed to scikit-learn's machine learning algorithm, right, as is. So we have to convert it to numbers first, meaning word to vec, like thing, meaning vectorization of text of the whole tweet, and then output as 0101. Now we are in the machine learning domain. All the numbers 0, all the numbers 1, numbers 0, 1. So now this is the trainable data set, right? From tweets, we have converted them to vectors, vectors with the output column. Now this is machine learnable data set. Just some code example. Once we have tweets, we typically clean it and then convert them to word to vec. As I said, Gensim is a very popular library, so it will convert text to numbers. Once it is converted to text to numbers, typical machine learning approach will come in the picture, right? It will, so for tokens of a tweet, it will give me vectors. And once vectors and labels are available, now any machine learning algorithm will do, not just logistic regression. You can put naive Bayes, support vector machine, anything. And you can build a tweet sentiment classifier. Guess what? 20, 30 lines, that's about it. But that's what we saw. We saw the whole thing. The theory, the idea behind all these things. All right. That's what I wanted to cover. Because almost all NLP modern applications are based on vectorization. So it is immensely important to understand the theory or the need or the approaches behind all these things. All right. By the way, this is a very vast field, many approaches, and almost no approach is perfect because language is ambiguous, language is very hard. And so its vector representation also is not perfect. But still, better and better approaches embedding models are coming day by day. Thank you.